guys, today we're going to explore the States of Matter simulation by PhET Colorado. When you open the simulation, you're given the options of selecting states or phase changes. We're first going to click on states. At the top right corner listed are 4 atoms and molecules to experiment with. There's neon and argon, 2 of 6 of the noble gases. Then there's oxygen, 1 of the diatomics, and the infamous H2O, which is water. Right below these atoms and molecules, we'll find the 3 states of matters: solid, liquid, and gas. Let's take a look at water. As you can see, when we click on the different states, the molecules change in how close they are to each other and their movement. Solid water, known as ice molecules, are tightly packed together by strong forces of attraction and are held in a fixed position. Because of this, solids have a definite volume and shape and don't really move much. Liquid water molecules, on the other hand, are packed close together as well and has volume too, but as you can see, they're less dense and have no fixed shape, allowing them to freely move. And gas water molecules, aka vapor, just go anywhere they like. Over here, you're able to control the temperature of the container, dragging up for heat and dragging down to cool it. Regardless of each state, the H2O bonds are still together, meaning whether we freeze it to a solid or sublimate it to a gas, it's still water, and this is only a physical change, not a chemical change. In this corner, you're able to change whether you want the temperature to be measured in Celsius or Kelvin, but we're just going to leave it in Kelvin. And down here, we're able to pause the simulation to take a closer look at the state the molecules are representing. And we can also press and hold here to have the molecules move in slow motion to analyze their movement patterns. Now, let's take a look at argon in its solid state. Solid argon particles are essentially bound together in a compact state. If we want to break the intermolecular force that is holding them together, we would have to increase the heat of it. Because temperature is a measure of how fast the molecules are moving, a higher temperature, of course, would increase the speed of these molecules. Now, as we rapidly heat it up, the state of argon changes from solid to liquid to gas. And of course, when we cool it down, it goes from gas to liquid to solid. We can see that it's a solid at 43 kelvins, but the particles are still slightly vibrating. If we put the temperature to their lowest energy points, known as absolute zero, which is 0 kelvins or negative 273.15 degrees Celsius, they don't stop moving completely, but move so slightly you can barely even see it. Now, we can go to liquid at 86 kelvins. In the liquid state, though the particles are somewhat together, you can see that they're somewhat jumping away from the pack. Some are jumping away from the pack. This kind of movement is what allows liquids to have a definitive volume while also being able to take up the shape of their container. Gases, at the other hand, at 189 kelvins, the particles move independently and have no definitive volume, which allows them to expand or shrink to fill whichever container they're in. This is why we are able to compress gas. Now, let's go to phase changes, which is just a term to describe transitions between solid, liquid, and gaseous states of matter, which we already looked at. To be exact, we have 6 phase changes. There's 1, freezing, which is liquid to solid, melting, which is solid to liquid, condensation, which is gas to liquid, vaporization, liquid to gas, sublimation, solid to gas, and deposition, gas to solid. To increase the pressure, we drag the lid down, and to decrease it, we drag it back up. As pressure increases, the temperature also increases, and vice versa, as pressure decreases, temperature decreases as well. This is because of Gay-Lussac's pressure-temperature law, essentially stating that the pressure of a given amount of gas held at a constant volume is directly proportional to the Kelvin temperature. An increase in pressure and temperature means an increase in kinetic energy, which is why we see the particles moving more rapidly as they strike the surface of the container with more force. On the side, we notice a pump that adds more particles to the container. Due to Charles' volume temperature law, as we continue to add more particles, aka increase the volume, the temperature increases as well. To sum this up, if volume increases, temperature and pressure does as well. And with this increase, we are able to see melting, solid to liquid, vaporization, liquid to gas, and or sublimation, solid to gas. Vice versa, when we decrease volume, temperature, and pressure, we see either condensation, which is gas to liquid, freezing, liquid to solid, and or deposition, gas to solid. All of this is shown in the phase diagram graph at the side. Cool little thing about pressure. When we drag the lid down too far, it completely explodes away just like this. This increase in heat and pressure increases the molecule's average speed until it's too much for the container to handle, so it just explodes just like that. That is the end of PhET state of matter simulation. By now, you should have learned the 3 different states of matter, solid, liquid, and gas, and the reason for the movement patterns, as well as the 6 types of phase changes and how change in pressure, temperature, and volume affect them. Thank you for listening.